You've watched your kid build towers, solve puzzles, navigate entire imaginary worlds, so why should learning to code feel any less hands-on? I'm Dr. Priya Mehta, and today we're talking about how to choose the right screen-free coding kit based on your child's actual developmental stage, not just the age range printed on the box. You're listening to the STEM Lab podcast. Quick note before we dive in. Everything you're about to hear, the research, the data, the script, it's all written and verified by real human authors. The voice delivering it? That's AI generated. Just wanted you to know. Now, if you're a regular listener here, thank you for coming back. These episodes take real time to put together, and it genuinely matters that you're here. If you're new to the show, hey, welcome. Glad you found us. We drop new episodes every Monday, Wednesday, and Friday, so you'll have plenty to work through. All right, let's get into it. Today we're talking about how to choose screen-free coding kits based on your kid's actual readiness, not just the age printed on the box. Learning how to choose screen-free coding kits by age doesn't mean you're sacrificing rigor or future readiness. It means you're honoring where your child is developmentally, while building genuine programming logic through hands-on exploration. In this guide, you'll learn how to match screen-free coding tools to your child's cognitive readiness, identify which tactile programming systems actually prepare them for industry-standard languages, and build a progressive learning path from preschool sequencing all the way to middle school algorithm design. This process takes about 20 minutes to complete your first assessment, and you don't need any specialized background. Let's start with what you'll need before you begin evaluating these kits. First, your child's current age and any previous exposure to logic games like puzzles, pattern games, or board games with rule systems. Next, make a list of the computational thinking skills you want to prioritize. We're talking about sequencing, loops, conditionals, functions, and debugging. You'll also want to think about your home learning environment specs, available floor or table space, minimum 2 by 3 feet for most kits, storage capacity for multiple components, and whether siblings will be sharing resources. Consider your budget allocation and tolerance for consumables. What's your one-time purchase ceiling, and how willing are you to replace batteries, paper coding cards, or activity booklets? Think about compatibility requirements. Does the kit need to integrate with future tools like Arduino IDE, Scratch, or Python environments? And finally, durability expectations. How often will this get used? Daily versus weekly? How many children will be handling the components? Do you need something that'll last 6 months or multiple years? Now, let's talk about understanding developmental readiness markers, not just age ranges. Most coding kit packaging lists ages 5 and up, or ages 8 to 12, without explaining what cognitive milestones those numbers actually represent. That's frustrating when your 7-year-old might think like a 9-year-old, or your 10-year-old needs more concrete manipulation than abstract symbols. When you're learning how to choose screen-free coding kits by age, focus on developmental indicators instead of birth fake handles. For ages 3 to 5, look for kits that teach directional sequencing, forward, backward, left, right, without requiring symbol recognition. Your child should be able to follow 3 to 4-step physical commands before a coding toy makes sense. The Cubetto playset uses wooden blocks and a tangible programming board, perfect for this stage, but some children find the fixed grid limiting once they master basic sequences. Check the link below to see the current price. Ages 6 to 8 mark the transition to symbolic representation. Children can now map abstract icons to actions and predict multi-step outcomes mentally before executing. Kits with coding cards, symbol-based commands, or color-coded instruction sequences fit here. They're building the same sequential logic used in Scratch's block-based programming, which becomes relevant when you're ready to transition from screen-free coding to Scratch and Python programming. Ages 9 to 12 require conditional logic and debugging challenges. At this stage, screen-free kits should incorporate if-then scenarios, loop optimization, and intentional error correction exercises. Without these, your child will outgrow the kit within months. Look for systems that let them write increasingly complex programs using physical components, essentially pseudocode made tangible. I've seen parents skip this assessment and hand a brilliant 4-year-old a kit designed for 7-year-olds, then wonder why frustration erupts. Developmental readiness isn't about intelligence, it's about cognitive infrastructure. Next up, identifying core computational concepts the kit actually teaches. Not all screen-free coding kits teach genuine programming fundamentals. Some are themed toys with vague STEM learning claims. Others are rigorous logic trainers that directly prepare children for text-based languages. Evaluate each kit against these 5 computational thinking pillars. First, sequencing, ordering commands. Every screen-free kit should teach this. Check whether sequences are fixed, like following a printed path, or open-ended, where you design your own challenge. Second, loops, repeating actions. Does the kit include a physical repeat mechanism? Can your child program move forward 3 times without placing 3 individual forward commands? This distinction matters. It's the difference between rote memorization and algorithmic efficiency. Third, conditionals, if-then logic. Rare in beginner kits, essential for advanced ones. Look for scenario cards, sensor-triggered actions, or rule-based challenges that change the robot's behavior based on environmental conditions. Fourth, functions, reusable command groups. Can your child create a custom dance move sequence and call it repeatedly? This abstraction skill directly maps to function definition in Python and JavaScript. Fifth, debugging, identifying and fixing errors. Does the kit encourage trial and error iteration, or does it simply mark answers as wrong? Quality screen-free coding tools make debugging visible. Your child sees where the robot deviates from the intended path and adjusts the command sequence accordingly. The Code and Go Robot Mouse activity set excels at sequencing and basic debugging for ages 5 to 7, though it lacks loop and conditional support, making it a foundation tool rather than a complete curriculum. Check the link below to see the current price. Understanding what screen-free coding really means helps clarify which features matter most. Now let's assess tactile interface design and manipulation requirements. Fine motor skills vary wildly across age groups, and a coding kit's physical interface can either support or sabotage learning. This is where developmental psychology meets industrial design. For ages 3 to 5, chunky, grippable components are non-negotiable. Your child should be able to snap, press, or insert coding pieces without adult help. Wooden blocks, large snap-together cards, and palm-sized robots work well. Tiny arrow tiles or fiddly connector pins create frustration that has nothing to do with computational thinking. You're just fighting dexterity limitations. For ages 6 to 8, transitional interfaces that combine tactile and symbolic elements work beautifully. Coding cards you physically arrange in sequence, magnetic tiles, or punch-out command strips give the satisfaction of manipulation while introducing abstract representation. Watch for card durability. Laminated or thick cardstock survives repeated use. Thin paper doesn't. For ages 9 to 12, at this stage, the tactile element should add value, not just provide novelty. Physical programming boards that let kids write complex algorithms using modular pieces, essentially unplugged versions of visual programming environments, prepare them for block-based coding better than purely digital alternatives. The interface should feel tool-like, not toy-like. Here is a lab specs consideration. Check whether components require batteries and how many, whether they're replaceable or rechargeable, and whether the kit functions entirely offline or requires app setup, which technically violates screen-free learning. Some unplugged kits sneak in tablet dependency for setup or validation. Read fine print carefully. I've watched a determined 5-year-old spend 20 minutes trying to align coding tiles precisely enough to trigger the sensor, tears building, while the actual programming concept sailed right past.
The wrong interface steals cognitive bandwidth from learning. Moving on to mapping the kit to your child's progressive learning path. Understanding how to choose screen-free coding kits by age means seeing beyond individual products to skill progression architecture. No single kit should be a dead-end investment.
Define your child's current skill tier. Tier 1, ages 3 to 5, concrete sequencing. Forward, backward, turn commands. No symbolic abstraction. Tier 2, ages 5 to 7, symbolic commands. Icon-based or color-coded instructions, introduction to loops. Tier 3, ages 7 to 10, multi-step algorithms, conditional logic, function creation, intentional debugging exercises. Tier 4, ages 10 to 13, computational modeling, complex state machines, nested loops, optimization challenges. Now, identify bridges between tiers. The best screen-free kits offer expandability, add-on challenge cards, advanced activity booklets, or companion products that increase complexity without abandoning the core system. This matters tremendously for budgeting. Buying 3 progressive kits from one system costs less than replacing incompatible products every 18 months. Ask yourself, does this kit prepare my child for the next learning milestone? If your 6-year-old masters a sequencing robot, will the concepts transfer when you introduce block-based robotics programming or Arduino boards? Some screen-free systems deliberately mirror Scratch's command categories. Those are your high ROI investments. Watch for compatibility dead-ends, proprietary coding languages or closed ecosystems that don't connect to industry-standard tools like Scratch, Arduino IDE, or Python limit your child's trajectory. The kit should be a stepping stone, not a silo. Learning Resources Botley 2.0 offers expansion packs and increasing challenge complexity, making it a strong Tier 2 to 3 bridge option, though some parents find the obstacle pieces feel flimsy after months of daily use. Check the link below to see the current price. Let's talk about evaluating lab specs for durability and practical use. Screen-free coding kits live on the floor, get stepped on, and endure the creative chaos of actual childhood. Lab specs determine whether your investment lasts 6 months or 6 years. Power requirements. Battery-operated robots need clear documentation of battery type, AA, AAA, rechargeable, quantity, and estimated lifespan per charge. Calculate replacement costs. Some kits drain batteries weekly. Rechargeable options cost more upfront but eliminate consumable expenses. Fully mechanical kits, no electronics, never need power but offer limited interactivity. Component durability. Cardboard coding cards won't survive toddler siblings or enthusiastic 7-year-olds. Plastic tiles crack. Wooden blocks endure decades but cost more. Check user reviews for failure points. Do wheels snap off? Does sensors stop responding? Does the main board survive drops? Storage and organization. Kits with 40+ small pieces need thoughtful storage solutions. Does the kit include a storage container, or will you buy bins separately? Can your child independently set up and clean up, or does component sprawl require adult intervention every session? Expandability. Can you purchase additional robots, extra coding cards, or new challenge sets? Are these readily available, or do discontinued products leave you stranded? Noise levels. Some coding robots beep, play music, or announce actions. That's engaging at first, then maddening. Check whether volume controls exist or whether you can disable sound entirely. Offline functionality. Truly screen-free kits require zero app or computer interaction. Some unplugged products need initial setup via tablet, then work independently. Clarify this before purchase if you're committed to completely device-free learning. For building a complete home STEM lab, these specs determine whether coding activities integrate smoothly or create logistical friction that erodes daily practice. Now, identifying subscription dependencies and hitting consumable costs. One-time purchase coding kits offer predictable costs and permanent ownership. Subscription-based models provide curriculum progression and new challenges monthly, but create ongoing expenses and access dependencies.
Ask these critical questions. Does the kit function fully without subscriptions? Some companies sell hardware cheaply, then lock advanced features or activity guides behind monthly fees. Read product descriptions carefully. Phrases like includes 3 months of challenges or app membership sold separately signal subscription models. Are replacement parts available individually? Lost coding cards, broken robot wheels, or missing command tiles shouldn't require buying the entire kit again. Check manufacturer websites for parts availability and pricing. Do consumables replenish automatically or require manual reorder? Paper activity books, sticker-based coding challenges, or write-on, wipe-off cards eventually wear out. Factor replacement frequency into your budget. Can multiple children use the same kit simultaneously? If you have siblings, does the system support parallel play, or will you need duplicate kits? Some coding robots work with shared command cards, others require one controller per user. What happens if the company discontinues the product? Proprietary systems dependent on specific replacement parts become unusable once manufacturers stop production. Open-ended kits with standard components, generic coding cards, universal robot platforms offer better longevity. I've seen families invest enthusiastically in a screen-free coding subscription, then find the monthly cadence doesn't match their child's learning pace. Too slow for quick learners, overwhelming for kids who need repetition. Understand your flexibility needs before committing. Next, matching kit complexity to available parent support time. Screen-free coding kits exist on a spectrum, from plug-and-play, child-directed from day one, to structured curriculum, requires adult facilitation and lesson planning. Your available involvement time matters enormously.
Self-directed kits include clear visual instructions, intuitive interfaces, and built-in challenge progression. Your child unboxes, explores, and learns through trial and error with minimal guidance. These work beautifully for ages 6 and up with strong, independent play skills, or when you're juggling multiple children. Facilitated kits include parent guides, lesson plans, discussion prompts, and extension activities. They're pedagogically richer but require your active participation, at least initially. Budget 15 to 30 minutes of setup and guided exploration for early sessions, tapering to check-ins as your child gains confidence. Assess honestly, how much time can you realistically dedicate? A sophisticated kit that requires daily 20-minute facilitation will gather dust if your schedule doesn't support it. A simpler, self-directed option your child actually uses beats an advanced kit that feels like homework. Progressive independence is the goal. Quality screen-free coding kits scaffold from adult-supported to child-driven over weeks or months. Early sessions might involve working through challenges together. Later sessions find your child designing custom obstacle courses independently while you make dinner. Consider your own computational thinking background. You don't need programming expertise. Many parents feel intimidated unnecessarily, but you should feel comfortable reading the instruction manual and troubleshooting basic issues. Some companies offer robust online support, video tutorials, and parent communities. Others provide a thin instruction sheet and wish you luck. For families building comprehensive, progressive STEM learning paths, understanding your facilitation capacity helps you sequence learning investments realistically. Let's talk about testing alignment with future technical pathways. The ultimate question when learning how to choose screen-free coding kits by age is, does this prepare my child for real programming languages and industry-standard tools? Map backward from your long-term goals. If your child will eventually learn Scratch, ages 8 and up, prioritize screen-free kits that teach block-based logic categories: motion, looks, control, sensing. The command structures should feel familiar when transitioning to visual programming environments. If Python is your target, ages 10 and up, look for kits emphasizing text-like syntax representation, function creation, and variable concepts, even if expressed through physical tokens rather than typed code.
For Arduino and robotics engineering, ages 12 and up, screen-free foundations should include sensor logic, conditional responses, and physical computing concepts. Your child is learning to think about inputs, outputs, and system states, precisely what matters when programming microcontrollers.
Industry standard preparation. The best screen-free coding kits don't just teach computational thinking abstractly, they mirror the algorithmic problem-solving professionals use daily. Software engineers debug incrementally, optimize loops, and abstract repetitive tasks into functions. Your 7-year-old doing exactly that with wooden blocks is building career-relevant cognitive patterns. Ask manufacturers directly. What percentage of users transition successfully to screen-based coding? Do they offer bridge resources or transition curricula? Companies serious about progressive learning publish clear pathways showing how their products connect to subsequent skills. The coding concepts your child learns through tactile manipulation at age 6 become the intuitive foundation for text-based programming at age 11. That transfer isn't automatic. It requires intentional kit selection that honors continuity over novelty. Now for some pro tips and common mistakes. Pro tip number 1. Create a coding challenge progression journal where your child draws or describes each completed challenge. This visible record shows skill growth, maintains motivation during plateaus, and helps you identify when they've genuinely outgrown a kit versus hitting temporary frustration. I've seen this simple practice transform coding from just another toy into a documented skill-building journey. Pro tip number 2. Mix screen-free and screen-based coding rather than treating them as opposites. Use tactile kits for initial concept introduction, then reinforce with short scratch projects, then return to screen-free debugging challenges. The switching strengthens transfer learning and prevents screen time guilt. Common mistake number 1. Buying the most advanced kit available because my child is gifted or we want to challenge them. Cognitive readiness doesn't accelerate with ambition. A frustrated 8-year-old with a kit designed for 12-year-olds learns nothing except that coding feels impossible. Start one tier below where you think they are. Early success builds persistence. Common mistake number 2. Assuming screen-free means educational automatically. Some kits are well-designed toys with minimal computational depth. Others are rigorous logic trainers. Don't rely on marketing claims. Evaluate against the 5 computational pillars from earlier. Common mistake number 3. Neglecting storage and cleanup systems. Scattered coding components become invisible, then abandoned. Invest in labeled bins, designated shelf space, and a consistent code lab area in your home. Physical organization directly impacts engagement consistency. Common mistake number 4. Comparing your child's pace to siblings, cousins, or online testimonials. Some children grasp loops immediately. Others need weeks of concrete manipulation. Developmental variation is normal and doesn't predict future programming aptitude. Patience during foundational stages prevents conceptual gaps later. Let's hit some frequently asked questions. What age should kids start with screen-free coding kits? Children can begin exploring screen-free coding concepts as early as age 3 if the kit matches their fine motor skills and focuses purely on directional sequencing, forward, backward, turn, without symbolic abstraction. However, most children develop the sustained attention and sequential thinking required for meaningful coding activities between ages 4 and 5, when they can follow multi-step commands and predict outcomes mentally before executing physical actions. How long should kids use screen-free coding before transitioning to screen-based programming? Most children benefit from 12 to 18 months of screen-free coding experience before transitioning to visual programming environments like Scratch, typically around ages 7 to 8, though individual readiness varies significantly based on their mastery of core concepts like loops, conditionals, and debugging, rather than chronological age alone. The transition should happen when your child consistently demonstrates algorithmic thinking, designing multi-step solutions, optimizing repetitive actions, and debugging independently, not simply because they've reached a certain grade level. Do screen-free coding kits actually prepare kids for real programming languages? Yes, when chosen carefully, screen-free coding kits build the same computational thinking foundations: sequencing, pattern recognition, algorithmic problem-solving, and systematic debugging that underpin professional programming, though the transfer requires intentional bridging as children progress toward text-based languages like Python or C++. The key distinction is whether the kit teaches genuine programming logic structures, loops, conditionals, functions, or merely directional play. Only the former creates meaningful preparation for industry-standard coding environments. Are expensive screen-free coding kits worth the investment compared to free online coding games? Screen-free coding kits offer tactile manipulation and spatial reasoning development that purely digital experiences cannot replicate, making them particularly valuable for children ages 3 to 8 whose cognitive development benefits significantly from physical object manipulation, though they work best as part of a mixed media learning approach rather than as complete replacements for screen-based tools. The investment pays off most when kits offer expandability, durability for multi-year use, and clear connections to progressive learning pathways rather than serving as isolated novelties. To wrap this up, learning how to choose screen-free coding kits by age requires matching developmental readiness markers to specific computational thinking concepts, evaluating tactile interfaces against fine motor capabilities, and ensuring each kit serves as a bridge toward industry-standard programming tools rather than a dead-end novelty. Start by assessing your child's current cognitive tier: concrete sequencing, symbolic commands, multi-step algorithms, or computational modeling. Then select kits that teach genuine programming structures like loops, conditionals, and debugging through durable, offline physical interfaces. Factor in lab specs, including power requirements, component durability, storage practicality, and expandability options, while clarifying subscription dependencies and your available facilitation time. The right screen-free coding kit honors where your child is developmentally today, while building the algorithmic thinking foundation for text-based programming tomorrow, making it a skill-building investment, not just another toy. That's it for this episode of the STEM Lab podcast. Thanks for spending this time with me today. New episodes come out every Monday, Wednesday, and Friday, so you'll never be waiting long for the next one. If this episode was useful, I'd really appreciate it if you'd leave a 5-star rating and write a quick review. It genuinely helps other parents and educators find the show. And honestly, it's one of the best ways you can support what we're doing here. And hey, make sure you're subscribed or following the show so you get notified the second a new episode drops. See you next time.